Short. See, in the last class, as I discussed about the KCL law. KCL law means Kirchoff current law. Today's class, in this class, I would like to discuss that KVL law. KVL law means Kirchoff voltage law, or Kirchoff's second law is nothing but the KVL law. So this KVL law, sometimes it is also referred as the loop law. It is also referred as the mesh law, because this law is applicable for the loop, so therefore it is called as the loop. Loop is nothing but the mesh. Mesh is a closed path for flow of electric current, which is known as the mesh. Now let us see, before discussing about the KVL law, so I would like to give a hint for you so that you can design the statement of the KVL law. Let us see what is the mathematical expression of the KVL law. See here, so that is the summation of, mathematically, summation of EMF. Summation of EMF is equal to summation of IR product. Summation of IR product. So this is the mathematical expression of the KVL law. So this is also recently that is expressed in this forms also, that is summation of V is equal to 0. This is the alternate form of the KVL law. So let us see, based on these mathematical expression, how we can design, how we can state the statement of the KCL law. First I would like to discuss that in this format. With the help of this mathematical expression, I will go to design the statement of the KVL law. Let us see, statement is like this, statement. So this law is applicable for loop. So therefore, in a loop of electrical network, so you can write it as this is algebraic sum of EMF. E stands for the EMF. So you have to add up the EMF of the EMFs in the whole circuit. How many cells are there? Those EMF we have to add up in the circuit. Say for example, 2 cells are there. So 2 cells you have to add up according to by using the sign convention. So similarly, which is equal to what it says, that sum of algebraic sum of EMF. That is this part, left hand side of this mathematical expression, the algebraic sum of EMFs, that is E. Algebraic sum of EMFs, E, is equal to the algebraic sum of it is what? Sum of product of current and resistance. R stand for resistance, I stand for current. Current and resistance in the different part of the loop. In the different part or branch, different part of the loop. So once again, see here, this statement contains 2 parts, is it? See in the left hand side, you have to make the sum of EMFs. If say for example 3 cells are there, you have to make the sum of the EMF of the 3 cells by using the sign convention, which is equal to the sum of the algebraic sum of product of current and resistance. That means that, so you have to say for example there are 4 resistances are there. So you will find that 4 IR product. So you have to 4 IR product you have to add it. So 4 IR product, I mean the total IR product, which is equal to algebraic sum of EMF of the whole circuit. So this is what the content of this mathematical expression. Let us see once again based on this. So in a loop of electrical network, the algebraic sum of EMFs is equal to the algebraic sum of product of current and resistance. Why we are calling that product of current and resistance? That is I into R. So therefore it is a product of current and resistance in the different part of the loop. Say for example 4 branches are there. In each branch there is some amount of resistance, is it? So since current is flowing, you will find that 4 IR product in the whole closed circuit. So you have to add up the IR product. That IR product, algebraic sum of IR product, which is equal to algebraic sum of EMF of the EMF of the circuit. So in the alternatively you can say that, alternatively you can state that vice versa, the algebraic sum of IR product, is equal to the algebraic sum of EMFs in the different part of the closed loop. So this is the how to construct the statement of the KVL. Now let us see this how this is similar to the KCL law. KCL law means Kirchoff current law. So this is so that is summation of I is equal to 0. That is what KCL law. In that format only, in that format, this KVL also nowadays students are writing. So now let us see, that is the algebraic sum of voltages. V stand for voltages produced across the circuit element and cells is equal to 0. This is the alternate statement of the KVL law. So far we have studied that. So what is the statement of the KCL law and what is the statement of the KCL law? You have seen that mathematical expression of the KVL law. That is this is the first form of the KVL law. This is the second form of the KVL. Alternately, you can state like this also based on this. So how we can design? So in an electrical network or in a loop of electrical network, the algebraic sum of voltages produced across the circuit element and cell is equal to 0. This is the alternate statement of the KVL law. So far you have seen that statement and mathematical expression of the KVL law. So the significance of this law lies in its application. So KVL law, as you know that this KVL law is especially useful for the complicated circuit, is it? So first of all, I would like to construct a complex circuit. So for this complex circuit, how we can able to apply the KVL law? Let us see how we can apply means how to find the current, resistance, voltage in the different part of the complex circuit. This is what the analysis. I mean that by using KVL law, we can analyze the complex circuit. Analyze means you have to find the current, resistance, voltage in the different part of the closed loop. So let us see here. I would like to draw the complex circuit. A complex circuit is one which contains 2 or more circuit elements and 2 or more sources of EMF which cannot be reduced into simple circuit which is known as the complex circuit. Let us see. I would like to design such a circuit, is it, which can be which can be applied by using KVL law. We can find the what current, voltage, etc. So let us see here. So this is a very simple circuit. So this is a simple circuit. See, these are the four junctions are there. You can call that this is A junction, this is B junction, this is C junction, this is D junction. So you can say that A, B, C, D, A. It is a closed loop, is it? See, there are four branches are there. Each branch having some amount of resistance. Say that resistance is represented by a zigzag line. See, this is all the zigzag line which represent the resistance, is it? So this is the zigzag line which represent the resistance. In this branch itself, a cell is that. So this is the cell, the circuit symbol for the cell. The EMF of this cell is E1. This is a positive, whereas this is negative. Big vertical bar represent the positive, small element for the negative. So now this you can call that R1, resistance R1. Similarly, you can, so AD branch which contains some amount of resistance, this represent the R2, is it? Similarly, third branch, this branch which contains a resistor, which is which contains resistance whose values are 3, and in this branch itself you are inserting the what you can say that another cell whose EMF is what you can say that E2. EMF of the second cell is E2, is it? So this is EMF of the second cell is E2. Now BC branch which contain the some amount of resistance. Every conductor 1 or 2A, it contains some amount of resistance. Now it is R4. So as I said, it contains 4 resistors. So we are consider a circuit, a complex circuit which consists of 4 resistors and 2 cells, is it? So now you have to apply the KVL law. So before applying the KVL law, so you have to familiar the network rules, is it? So according to the network rule, first you have to see this complex circuit. Look at the complex circuit. Now first step is that you have to arbitrarily or preferably you have to show the direction of current from the positive terminal of the battery towards the negative terminal. So that means that you consider AB branch. In this branch the resistance is R1 and EMF of this cell is E1. So this cell sends the current in this direction from E12 towards the junction A. So this is, you can say that first cell sends the current I1, sends the current, say this is the I1, is it? Now you come for this AD branch. In this AD branch, say that current is moving what A to D direction. The strength of that current is I2. Similarly, this is the D junction. In this D junction, current is flowing. See that current is flowing. You can write it. See in this direction. Say in this branch, current is flowing from D to C. You can see D to C. See this, you can say that this you can call that I3. So now in this branch you can say that just I would like to change it here for the simplification. So you can say that. So this is in this branch current is flowing like this, is it? So this current I3, and once again in the CD branch, that the CD branch current is flowing like this. So the magnitude of current is I4. Resistance is R4, current is I4. So this is the this is what complete complex circuit. Now you see that. So first step is that you have to see whether the current direction is mentioned in the different part of the loop or not. This is in a loop. You start from this one point, again you will coming for same point. This is nothing but a loop. It is in a closed path, is nothing but the loop or mesh. Mesh is a closed path for flow of electric current. So now this KVL applicable for loop only, so therefore it is called as the loop law. So first step is that, that you have to show the direction of current in the different branches of the closed loop. There are 4 branches are there. In each branch, direction of current is shown by the arrowhead. So now second step, you can rotate this mesh either in the clockwise direction or in the anti-clockwise direction. For my convenience, I am rotating this mesh in the in the anti-clockwise direction. This shows the this mesh is rotating transverse in the anti-clockwise direction. Now what you have to do that? So before applying that KVL law for the complex circuit, so you have to familiar that sign convention. These are the you see that for all the resistors or cells, current is mesh is rotating from A to B always, is it? So how to take the IR product sign convention? Say that mesh is rotating from the A to B, but in this resistor current is moving from B to A. That opposite direction. If it is the case, IR product is taken to be positive. IR product is taken to be positive. Otherwise, it is taken to be negative. Otherwise, it is taken to be negative means current and mesh both are moving in the same direction. Then IR product is taken to be negative. So therefore here, mesh is moving from A to B. Current is also moving from A to B. That means that both are moving in the same direction. Then IR product is taken to be minus, negative IR. Similarly, as for the sign convention for the EMF of the cell, see you are traversing the mesh, you are rotating the mesh from A to B. Okay. So now what happened that if you if the potential will be fall as positive terminal to negative terminal, as you are moving from positive to negative terminal, if it is the case, whenever the potential fall, the EMF of the cell is taken to be negative. In this case, this is the higher potential, this is the lower potential. So therefore, EMF of this cell is negative. Okay. So similarly, you are traversing from A to B. So now this is the negative terminal, this is the positive terminal. You are traversing from the negative terminal of this cell toward the positive terminal. If it is the case, EMF of this cell is taken to be positive E. So these are the sign convention meant for the KVL law. Let us see how we can apply with the help of sign convention for this complex circuit. So first you consider, as I said, that there are 4 branches are there. Is it? First one AB branch, second is BC branch, third is CD branch, fourth one is DA branch. First of all, you consider any one branch. Start from AB branch. Is it? You are considering AB branch. In this AB branch, you are rotating this mesh. You are rotating this mesh in the anti-clockwise direction. So see what happened that here you are traversing from EMF of this cell. You are traversing from the lower potential to higher potential. If it is the case, EMF of this cell is taken to be what? Positive. So that means that EMF of this cell is plus E1. You see that here. So in this case, what happened that you see that so you are traversing from the lower potential to higher potential. So you are traversing from lower potential to higher potential. EMF of the cell is positive E. So therefore it is since the first cell is at E1 you are written. So now you come for the IR product. So in this case IR product, current into resistance. Current is how much? I1. Resistance is R1. You see that you are rotating this mesh in the anti-clockwise direction. Current is also moving in that branch in the same direction. If it is the case, if it is the case, IR product will be negative. I mean that the current will be moving from A to B. Mesh is also traversing from the A to B. So if it is the case, the IR product will be minus IR. I mean the negative IR. So here the magnitude of current is I1. So resistance is R1. So this complete what IR product. Similarly, you come for the AD branch. In the AD branch there is no cell. Just you have to multiply the IR product. See, you are rotating this mesh in the anti-clockwise direction. Current is also moving in the same direction. If it is the case, IR product is taken to be minus I2 R2. Minus I2 R2. Similarly, you come for the DC branch. In this DC branch, that is, you are rotating this mesh in the anti-clockwise direction. Current is also moving in the same direction. Is it? Current is also moving in the same direction. If it is the case, IR product is taken to be minus. That is minus I3 R3. Now, this branch contains a cell, that is second cell. So as I said that whenever you are rotating, whenever you are moving from the lower potential to higher potential, EMF of that cell is taken to be positive, is it? So EMF, that is plus E2, plus E2. Now you come for the, that is CV branch. This is the last branch. So this branch contains no cell, only one resistor and some amount of current is flowing. So you are rotating this mesh in the anti-clockwise direction. Current is also moving in the same direction. So therefore IR product is taken to be minus I4 R4, which is equal to 0. Is it? So now this expression can also be rewritten in this form. See, you can arrange this expression in this format also. So you have to add up the EMF of the different part of the loop. This is one cell, this is another cell, this is a positive lower potential to higher potential. So you can write it is E1 plus E2. Z. Now these all terms you are taking that side, which is equal to what you done. Just what you did, just you are added the what IR product. So all the signs will be going to change. That is sum of I1 R1 plus sum of I2 R2 plus I3 R3 plus I4 R4. You see that? So now this all the term, that is sum of I1 R1, sum of I1 R1, I2 R2, I3 R3, they are IR product, you are summed. I mean that you are added. You see, this is nothing but the algebraic sum of IR product, which is equal to, that is sum of EMFs in the different part of that loop. This is the what the content of the what loop law. Is it? So now, as I said it, this law can be written like this also, or you can write like this also. Now, as I said it, what is the significance of this law? As I said it, this law, it is based on the conservation of energy principle. So, what is the conservation of energy principle? I mean that energy of the charge, when you moving, say for example, you are starting from your journey. So, you are say that some charge possesses some definite amount of energy while the charge is at this point. This charge, after rotating and coming to this point, change in the energy of the charge will be 0. That is, I mean that. So therefore, the energy of the charge, it will be remains constant. So therefore, Therefore, Kirchoff's second law, it is based on the conservation of energy principle. You see. So now, so far we have discussed that what is that statement of the KVL law. KVL law means voltage law, Kirchhoff voltage law. One format, that is in a loop of electrical network, the algebraic sum of EMFs, which is equal to the algebraic sum of product of current and resistance in the different parts of the loop. There are four parts are there. You are made the product of IR product. You have added the product of IR product, which is equal to sum of the EMF of the different branch of the loop. Now, this is what the complete explanation of the part. Similarly, alternate statement you can state that V stand for the voltages. This is the what summation, the algebraic sum of voltages produced across the circuit element. So, resistance and this cell, where they will find that voltages. You have to add sum of the voltage produced across the circuit element, which is equal to 0. This format, it is similar to the what KCL law. So algebraic sum of current is equal to 0. So it is quite easy to reproduce. If you, that is, you can state that this form is quite easy to reproduce. That is, in an electrical network, in a loop of electrical network, the algebraic sum of voltages produced across the circuit elements is equal to 0. As I said that Kirchoff's second law, it is based on the conservation of energy principle. Now let us see sign convention also discussed. This is a complex circuit. As I said that complex circuit is one which contains the 2 or more cells and 2 or more circuit element, and which cannot be reduced into what simple circuit, which cannot be applied for which cannot be used Ohm's law, is it, to determine the current, resistance and voltage. So therefore Kirchhoff felt that two more formula laws he developed in order to deal with the what complex circuit. Now let us see, these are the sign conventions are there, is it. As I explained that how to take that, with the help of this kind of sign convention you can write the this equation. This equation is very useful while solving the problem. This equation is very useful. Now let us see, I would like to give one example, one numerical example, so that you will get the clear concept about the KVL law. Let us see, say this is an equilateral triangle. You consider an equilateral triangle. This is an equilateral triangle. So as you know that the circuit is an equilateral triangle in that format. This is what imagine that this is an equilateral triangle, right? So see here, there are three branches are there. There are three branches are there. From this branch, you can say that this you can call that A junction. This is B corner. This is C corner. So C, instead of calling C corner, you make it a C junction. So current will going to entering at the junction A in the circuit. Say that I is equal to 6 ampere of current it is entering at the junction A, is it? So on entering at the junction A, that current will be divided into two parts. So I1 ampere of current, it flows along AB direction. Say that I1, which is I1 is equal to I1, and this resistance is that, this resistance is say you can say that 2 ohm. Resistance of this is R1 is equal to 2 ohm. This again R1 is 2 ohm. So this is 2 ohm, this is 2 ohm, because this is not a junction. is it? Simply just you are bending the wire. So now these two resistors, they were connected end to end. So therefore you have to make the sum of the resistance of these two, which is equal to net resistance is what? It is 4. See, in this case, so that so this is what you can say that I2. See, this is also resistance is in this I mean that in this branch AC branch resistance is R2. So whose resistance is 2 ohm. So now question is that how much branch current in this branch, how much current is flowing? That is, this is I1 and I2. These are the branches of this closed loop. So you see that this main current entering at this junction, it is split into two parts and it take round and goes in this direction, that is I1 itself. In this I1, again I1, is it? So now this I2 and I1 together at this junction, they will meet at this junction and you will get once again main current, that is equal to 6 ampere. That is equal to 6 ampere. Now let us see how to find the what branch current. These are the two branches of this this circuit. Now let us see how to find the I1 and I2 by using the KVLR and KCLR. Let us see this example, in a beautiful example. So I would like to show, first of all you have to apply the KCLR at the junction A. So this is a junction is a point where 3 or more conductors are made. That point is known as the junction. So here in this branch, current is coming toward the junction, it's taken to be positive, whereas I1 and I2, these are the two branches are there. In these two branches, current is leaving from the junction. According to the sign convention, any current coming toward the junction is taken to be positive, whereas the current leaving from the junction is taken to be negative. So that means that I is main current is I is positive because current is coming toward the junction. Whereas I1 and I2, this arrowhead shows the directions, shows that current is leaving from the junction. That is minus I1 minus I2, which is equal to 0. Or you can rewrite this expression, that is I is equal to I1 plus I2. So that is main current is equal to sum of branch current. Main current is equal to sum of branch current. You see that I stand for the main current. So branch current is I1 and I2. These are the branch current. So basically you have to find the, you know that R1 and R2. R1 and R2, you know it. So how to find the